Okay, so good morning everyone. Thanks for coming to the first seminar of this academic year. And today we have the pleasure to welcome Franz Bauer from Chile. So Franz will stay with us for a month because we have the NECOS Sur grant. And Franz is an expert of AGN. And today he's going to talk about little red dots near and far.
Yeah. Okay, thank you very much. It's a pleasure to be here. So as Nico said, I'm from Chile, from the Universidad de Tarapacá, which in theory is, well, technically it's in the northernmost city in Chile, but I actually work in Santiago at the Institute of Higher Investigation. And so this is sort of one of my many hats that I sort of wear is trying to study AGN, in particular AGN near, AGN far, and the little red dots have been posing a significant sort of puzzle for us with JWST. And so I wanted to kind of outlay that to you guys. Many of you probably are not so familiar with little red dots, or are familiar only with them as being annoying. They fill up the archive, so you have to go sort of scroll through them, or they are taking all of the money and time from JWST. And so anyway, I'll explain why they're interesting, so hopefully you'll at least have a little bit of an appreciation for that. So these are some snapshots of little red dots from JWST's first surveys. So JWST launched. They did a bunch of deep surveys of the extragalactic sky. Because it's such a profound jump compared to other instruments, they found a bunch of new objects, right? And these were one of them. These were a surprise. And so they're sort of point-like objects that are read in the near-infrared bands of NIRCam and NIRSpec. And so JWST launched, right, and started sort of pumping out data. And this is the sort of literature on little red dots over the last 2 years. So you can see it kind of exploded. And there's several published papers and many sort of unpublished sort of things in press that have been going on, kind of all of this excitement. Okay, so what the heck are these things? So basically they have a very weird spectral shape. And so this is a spectrum from NIRSpec. And so you can see it in the UV. This is the rest frame wavelength. This is just flux in F lambda. They're pretty flat in the UV. And then they jump up right around the Bauer limit of 3,600 angstroms or so. And depending on which target you see, they might jump up by a little bit or a lot. So you have very steep Bauer breaks. And then they're sort of reddish, and then they kind of turn over a little bit in F lambda as you go into the near infrared. And this is unusual, particularly in the near infrared. And so people sort of picked them out in color diagrams because they didn't know what they were. We didn't have any local analogs of these things before. And so they then put them in NIRSpec, the MSA, and got spectra of them. And lo and behold, they find this really strange continuum. They find huge, whopping equivalent with emission lines that are broad, with full width half maxes of 1,000 up to 3,000 kilometers a second. And of course, broad lines, people automatically jump to the sort of thought that these are AGN, right? What can generate a line width of that sort of velocity? And a supermassive black hole is one of those things. So that was the first sort of interesting thing. We generally don't see such objects, such sort of AGN locally, or even at high redshift before. And so these are new sort of subclass of AGN. They're nearly point-like. They do show some sort of scruffy emission. You can see over here, right? There's a little bit of fluff over here, but they're dominated by point source. And so initially people didn't make any sort of point source selection, and then when they got spectroscopy of them, they ended up finding that the things that were more extended tended to be very extreme emission line dominated objects, but star-forming galaxies, whereas the point-like objects tended to be more these little red dots. And so they started making a selection based on the compactness of the object. So they're generally fairly compact, but part of that may also be a selection effect. As I mentioned, they have these broad permitted emission lines. They're about 1 to 3 decks below the standard quasars we detect from the ground. So this is the luminosity, the absolute magnitude in the UV. And so typically, quasars from the ground are in this range here, sort of minus 23, minus 24, maybe probing down to minus 22. The little red dots are now sort of in the range of, they can get up to sort of minus 22, but the bulk of them are sitting around minus 19, minus 18. So they're significantly less luminous by 1 to 3 decks compared to the past quasars population. Another thing that's sort of interesting is that if you start counting them, there are hundreds over, sort of hundreds of square arc minutes. You can compare this to the ground-based quasar catalogs at these similar redshifts. So these are all at redshifts of 4 to 6 to 8. And so the space density of really bright luminous quasars that we could detect from the ground is like a few per square degree. Right? So you compare hundreds of square arc minutes to a few per square degree. There's just a ton of them. And so it's sort of estimated that they might comprise, at these redshifts, up to 30% of the population of AGN, extrapolating down what we knew previously, and then sort of adding these in. And so this is the big deal, is that we didn't know about them before. Their SEDs are completely strange, and they might comprise a huge portion of the population. Right? And that's ultimately kind of why people went crazy about these things and why there are 100 papers on them in the last 2 years, why people are pouring hundreds of JWST hours into them. And of course, they're very faint. They're at high redshift. You can only really approach them in the rest frame optical, which at redshifts of 5 to 8 is the near infrared, which is where JWST is the winner in terms of what it can do. Okay, so as I mentioned, they were photometrically selected initially, and so they just did color cuts in near-infrared bands, right? So some cut here, and we select the reddest things. And then we go and observe them, and we start to see what's going on. And typically, as I mentioned, the ones that were point sources tended to have the broad emission lines in the permitted sort of band. So broad Balmer series, broad Paschen series, broad helium, et cetera. And then they also sort of ended up making a point source selection. And so typically they want most of the flux to be in the sort of 0.2 arc second band compared to 0.4 arc seconds or 0.5. This is one selection that selected many hundreds of candidates over 640 square arc minutes. Here's another one that chose a slightly different path of doing multiple bands and fitting a slope, and then looking at sort of slope, UV slope to optical slope, and kind of fitting a range there, and again getting a color. And the idea is to find something that has an inflection point. So something that is basically sort of bluish in the UV and reddish in the optical, right? And that avoids, this is sort of the brown dwarf region. These are normal star-forming galaxies, and so they kind of pick out this region here. And then again, some criteria that's picking out roughly, very compact sources as well. This is the R effective radius. Finally, there's this is trying to go bluer. So Bauer, for instance, tried to find bluer sources, and he kind of released the criteria a little bit, trying to find these gray sources here, which were missed by the previous selections. So there's lots of work in terms of the demography of what the population actually is. Are there, for instance, going back here, right? I mean, are we missing some portion of the population because of the selections that have been done to make a very strong color cut? And then finally, people, once JWST started delivering spectra with the MSA on NIRSpec, they now had spectra of hundreds, thousands of objects. And people started doing blind studies of the things that were selected and started to do spectroscopically selected objects. And there, the benefit is that you can avoid emission lines and just look at the continuum slopes and use that, because of course the emission lines are very high equivalent width, and so they can dominate the selection, and they can kind of push in very extreme emission line objects into the selection. So they did that, and they find, a subset are sort of contaminants, but a majority of the photometric selected objects are sort of legitimate. And this is just sort of highlighting the photometric slope in the optical versus the spectroscopic slope in the optical. And generally, they're pretty good, but you can see that there are some sort of portions which skew from the one-to-one line. And there are sort of problems with the spectroscopic sort of selection. One, JWST doesn't have as much, obviously photometry, you can do everything in the field. Spectroscopy, you're limited to what was observed. And so generally, there's about 60 to 80 broadline objects that are in the archive, of which only about 40 are LRDs. So it's a much smaller sample by an order of magnitude. But it's sort of more secure. The problem is also that you can have the sort of MSA slit might be centered over it, but it might also not be, and so you can have slit losses, low signal noise, other problems that come in there. So those are the selections that have been done so far. And so, again, to highlight sort of why these are so weird, these are the spectra of several of the LRDs. This is the spectra of quasar at a similar redshift. This is a sort of type 1 quasar. This is a reddened quasar from DESI. And this is reddened by sort of an AV of 0.5 or so, so not much. You can see that these things are much, much, much redder, right? And so typically, one needs sort of an AV of 3 to 5 in order to redden this by that much. But then there's this excess blue which comes out, right, which isn't being killed. And so we have to explain that. And so typically what people will do is, you end up having to have some sort of composite SEV to fit this, right, because you can't fit it with one monolithic sort of SED model. By the way, if you have any questions, just feel free to ask them. I can answer them. OK, and so just another way to sort of look at that is the following. So these are different AV laws, and this is the sort of AV requirement as a function of wavelength. And so you can see sort of, they sort of follow this trend up to about 3,000. And then around the Balmer break, they flatten off when they should be sort of rising up like this. And so these are very hard to fit with a monolithic population is the main point. And so typically what people will end up doing is fitting a composite of something that will fit the blue and something that will fit the red that are completely separate. This could be a star-forming galaxy, a blue unobscured star-forming galaxy population combined with an obscured AGN. This could be an obscured population of stars with an unobscured population of stars. This could be an unobscured AGN with an obscured population. I mean, people have tried all these different combinations. I'll show you much, much later even some more exotic models of sort of how you would fit this. And you can see that the residuals aren't great, particularly around the Balmer break in general. And so it's been really hard to fit this with traditional models. And so, for instance, if you throw Segal at these objects out of the box, it will fail very hard because it needs multiple components in a non-monolithic sort of way. This is just, again, I took a spectra from about 30 different objects, and just to highlight the sort of differences as a function of, this is just in luminosity in F nu now, not in F lambda, but just to highlight kind of, you have this sort of UV area, you have a rise here, and then this flattening, and the points out here in sort of rest frame 2, 3, 4 micron start to get very sparse because there's not much MIRI data available for these objects. And so the point is that you get a variety of different sort of Balmer sort of cuts, and then you have a huge variety here. And maybe it's a little bit easier to see if you normalize all of this. And so I just can normalize it to about 5,000 angstrom range. And so now you see this tightens up, obviously because we're normalizing it there. But you see a huge diversity in the UV, right? Not as much diversity, but a little bit of diversity in the near infrared. And really not much diversity across most of the red portion of the optical. And partly this is from the normalization, but the point here I wanted to make is that these components are probably separate, right? So they're not connected in a very physical way. This could, again, be star formation from the galaxy. This could be from some obscured compact region. And so they don't necessarily have to talk to each other or know about each other. Right? And this is probably what's driving a lot of this diversity here. OK. So people have looked at the different selection effects. In general, the V shape, the sort of rest optical point source, and the broad Balmer lines are a dominant sort of component in this Venn diagram. You do find sources that just have one, maybe not all of them, but largely the selection seems to work. What's interesting is that although most of them have broad lines, if you look at the BPT diagram for them, right? So if you take the narrow lines, the oxygen, the rest frame BPT in the optical, so you take the oxygen 3 and H beta versus the nitrogen 2 when you can resolve it from H alpha, these LRDs tend to lie in a region of phase space in BPT, which is sort of dominated by galaxies. Typically, this is a low metallicity region when we look at local objects or even high redshift objects. So they're not sitting out here. So even though they have these broad lines, the sort of narrow lines are being sort of powered by potentially star formation or something that has a low ionization. Right? It doesn't have very hard UV photons. And so this is interesting because we have this AGN, but then it doesn't have a strong UV component, a hard UV component to drive the ionization. If you turn these full width half maxes, so the typical, as I mentioned before, the full width half maxes are ranging from a sort of barely broad to pretty strongly broad at 3,000 kilometers a second. They have really large equivalent widths of 300 to 800 angstroms. And then the broad to total ratios are typically 30 to 80%. So they're sort of dominated by the broad lines in many cases. And so if you turn those into black hole masses, which you can do following scaling relations, I don't necessarily trust the scaling relations, but nonetheless, the entire community has adopted the scaling relations and uses them gratuitously. If you do that, you find black hole masses that kind of in the range 10 to the 6 to 10 to the 8. Right, so they're really pretty large objects if you trust the full width half maxes of these. And we have completeness issues, so as you go down to 10 to the 6, you may not be able to resolve that. And also as you go down in magnitude, you may be missing some components of that. And so you can extrapolate the numbers of these objects even further because you're missing some portion of them. What is also interesting is that in addition to the broad permitted emission lines, we see broad absorption. And this is super unusual for AGN. In fact, we usually do not see this in AGN. And so you can see here, for instance, very strong absorption out to sort of many hundreds, out to 1,000 kilometers a second in some cases. You can see absorption in helium-1. Here's another sort of absorption around H beta, absorption around H alpha. This is actually a spectrum taken from the ground of one of these, of the brighter objects, this one in particular here. And in fact, it's one of the only instances where we've been able to confirm something with JWST from ground-based sort of observations. But you can see the signal noise here is not very good. You can still see the absorption, but this is much cleaner. And so these absorption profiles are interesting because they require a relatively, I wouldn't say huge column density of material in front of the broadline region, but something on the order of 10 to the 10 in terms of hydrogen density. And also some sort of modest ionization parameter. And so this has led people to kind of postulate that there's this envelope of material that's sitting outside of this compact object. And so they will model it as sort of a cocoon envelope or a dense atmosphere, which again is super bizarre if you've known sort of normal AGN, because they don't have this. They don't show this at all, ever. And so with this cocoon, you can get this really strong Balmer break. And so people started modeling this. And so the cocoon is essentially, you can think of it as an outer stellar atmosphere at sort of maybe 300 AU or 1,000 AU with a temperature of somewhere around 5 to 9,000. And that allows you to reprocess most of the emission from the disk and sort of reorganize it so it's mostly in this form. So this is what people have come away with, is that these objects have these outer envelopes. And they're kind of these cocooned black holes, supermassive black holes. Then you can add a UV component, this separate component, and fill in this flat blue UV emission. Okay. This atmosphere also prevents strong feedback, so it kind of absorbs the feedback that you would get from a typical AGN, and you end up with a sort of relatively high black hole mass compared to maybe the stellar component that might exist in the host. Now, we do see outflows, right? I just told you we saw outflows of hundreds of kilometers a second. So there's an inconsistency here that is not fully resolved yet, but this is kind of where the community has gone. And lots of different people have come to the same conclusion. Okay, is there a question in the back? No, okay. Going to their compact nature, so typically you can measure most of the light in the effective radius to be somewhere with a resolution of JWST in the range of 80 to 300 parsecs at redshift 5, 8. And if you kind of extrapolate this, if this was all stars, right, you extrapolate this and this has a stellar density of something like 10 to the 5 solar masses per parsec cubed, which is insane, right? This is much higher density than globular clusters, anything like that. And so having a compact object like an AGN there resolves that issue. But if you wanted to try and explain it all with stars, it's hard. And so these are just different sort of stellar densities that you might, stellar surface densities that you might see for this compactness. And these are mostly upper limits because JWST hasn't actually resolved them. They're just point sources, right? So they could go even further down. As I mentioned, some of these have some fluff, right? But it's not a really strong dominant component. It's typically sort of less than 10%. Generally, this emission might be a little bit bluer than the actual compact object sort of light. But if you model it, you might end up getting, typically this is a star-forming region that's extended. Generally have, fits well with something that has a low metallicity and a pretty high ionization factor. And so this has become pretty typical. One of the caveats here, of course, is that we're working at redshift of 4 to 8, and surface brightness dimming is a real problem, right? Because it goes as 1 plus c to the 4th power. And so basically, there are some selection effects. So as a function of redshift, you end up sort of pushing the sort of limits, and so you end up finding that you need a very, very, very strong limit to detect any fluff around this object if it's at redshift 8, whereas you might be able to detect it with a much brighter sort of surface brightness at, say, redshift 3. And this comes back to the selection that we were talking about, where most of, they're selecting things that are point-like. And as you'll see in a little bit, we're seeing that the density of these objects falls off as you go to lower redshifts. And so there is a potential worry that we're having some selection effects in here, although people have tried to mitigate that. We also have to think about the fact that as the universe evolves from redshift 10 to redshift 2, you're going to have an evolution of the morphologies of objects. So the disks of objects or the spheroid components are going to grow over time. And so you also have that sort of coming into all of this as well. And people have postulated that these sort of very compact objects, right? So you still have most of the light there. Some of it might be from a star cluster or a spheroid that's very, very compact, and then you have an AGN in the center. that star cluster is still very compact, or that spheroid is very compact. And so people have talked about maybe these LRDs are forming from the lowest spin halos out of the distribution of halos. And so maybe they're just a consequence of that. But it's sort of unclear. When you combine the black hole masses, which we estimated from the sketchy relations, and the stellar masses that we estimate from the compact sort of deconvolution of the SED, you end up with this result here, where this is kind of, you can put an upper limit on this because it's just the total amount of light you have. But the more you fit the higher the fraction of light you put towards the AGN, the more it's going to move off of this. And so most of the objects that people have found have been sitting well off of the local M sigma or M black hole M star relation, which is something like this at sort of redshift of 1. It's well down here in the local universe. And so they're really, really off of this, and people have made a big deal about this. So essentially you have overmassive, supermassive black holes sitting in kind of dinky galaxies. And one sort of puzzle that we haven't really figured totally out yet is what happens as these things evolve to lower redshifts, where we see not so many of these things. Or at least as of yet, we haven't found a huge population of objects which are overmassive, right? We do have some, dwarf spheroids sometimes have heavy black holes compared to the local relation, but the number of them is not sort of dominant like it is here. And people have postulated, maybe this evolves, and basically as a function of time, the very compact spheroid component that's here right now will puff up and get bigger, and maybe also have some sort of accretion, and maybe will kind of, sort of local, sort of settle into something that's more equivalent with the local relation. But it's a big part of the puzzle. Another aspect of AGN is variability, and what's sort of puzzling here is that to the extent that we can understand the calibration errors of JWST, in general, most of these objects don't show any strong variability. Typically, within about 20%, they don't seem to vary. Now, I told you that the UV component is maybe coming from, say, the star formation component, and so maybe we don't expect the UV to vary, but this, we expect to vary by some amount, and really we don't see any strong variability from that, and we're not sure what to make of that. So yeah, this is another sort of version of this. These are sort of calibration stars, and you see flux changes of sort of 20%, maybe 50% in some cases, but this is rare. This is only in 8 out of 300 LRD candidates. So it's a very small portion of the population might be varying at all. When we look at the X-rays, generally the X-ray emission is really outclassed by the depth of JWST. But nonetheless, we have some deep fields that JWST has looked at that also have deep X-ray observations. And so these are some of the constraints from that. And so this is just the X-ray emission versus the, this is H alpha, which I clipped here. But this is basically H alpha emission. And locally, we see a relation between these two, which is not quite linear, but it's sort of within, it's basically one deck off. And so most of the constraints are sort of sitting at that limit already and are upper limits. So they're definitely below that. If you do stacking of all of these, you find that the stacking results are sort of one deck below this local relation. So these things seem to have an X-ray deficit, which is, of course, bizarre for AGN because we know that AGN have a very kind of consistent X-ray to UV ratio across basically redshift 0 out to redshift 7 with the ground-based AGN that we know of. And so this is unusual, right? And so to explain this, people invoke one option is super Eddington accretion, where you have basically a puffy disk and a lot of the inner light that's generated, so this hard UV light and the X-ray gets trapped in the material, which then gets accreted. And so essentially the black hole eats the light, and so it never gets out. And so that's one way of getting rid of this or explaining this X-ray weakness, and also explaining the weak UV that I mentioned before with the line ratios. Another way is to have it be heavily obscured, but at these redshifts, the K correction is such that we're actually moving towards harder X-rays, which are harder to obscure. And so we need really pretty insane column densities. If you convert this to AV, we're talking about AVs of 100, right? So they're huge compared to what we're seeing in the optical regime, which is already large, but I mean, we're still orders of magnitude different. Or maybe we're overestimating the supermassive black hole masses, the bolometric luminosities, and so forth. So that's another possibility. Okay. If we move to the sort of lower wave bands, or the sort of less energetic light in the infrared, we also see a lack of infrared, which again is puzzling, because typically AGN have tori, and those tori will reprocess some large fraction of the AGN light, and you'll end up seeing that in the mid-infrared or in the far infrared. And so the constraints, typically again from stacking, are such that we can't put too much dust there. And so you can see here, for instance, this is just sort of SED of a typical LRD, and the limits are such that we can kind of model it with a relatively hot dust component that's not super heavy in dust, and is kind of missing information here, and is missing the soft, or like the cooler dust component that we would typically see in a large star-forming galaxy. And so people have done various sort of modelings of this, but in general, the amount of dust that we can live with is relatively low compared to normal AGN or normal star-forming galaxies. And so, right, they could be reddened, but they have to have basically a kind of weird dust distribution to do so. The alternative is that we have this envelope which reprocesses most of this in the optical, and then it doesn't actually get out to the infrared to need to be reprocessed there. And so that kind of helps explain some of this. Again, this is just a stack from Cosmos kind of showing this. And so these gray SEDs are typical objects at similar redshifts. This is an AGN. Actually, let's see. I think I got that wrong. Let's see, it's here. Okay, so this thing is an obscured AGN in solid, which you can see has a very hot component with a huge silicon absorption line, and then the sort of brown grayish thing is a star formation object. As you can see, it has a huge cool dust component, both of which would be excluded by the average stacking data from Cosmos. And so you can still get away with some dust with some sort of range of luminosities, but it generally is lower than a typical object at the same redshifts. And then again, the X-rays are sort of somewhat constrained if we're assuming that the UV is actually here and we're seeing just a fraction of the light in the UV from the X-rays, or from the sort of UV component of the disk. Okay. Finally, in terms of demographics, I mentioned this a little bit before, but when we start to count up all of these objects, we get limits like this as a function of absolute magnitude in the UV, and we can compare this to the galaxy magnitude function. And this is orders of magnitude, but this isn't much, right? So we're talking about maybe 5% of all galaxies end up being LRDs somehow, which is kind of an insane amount. So they're relatively common. If you look at as a function of redshift, right, they're relatively common at redshift 10, 8, and then they drop like a rock as you go to redshifts of 2. And so there's a very strong evolution that we're seeing that is probably beyond just selection effects. Right, I mentioned that there's the surface brightness dimming issues. There's the fact that we might be excluding some objects because we're requiring point sources to kind of avoid contamination. This is too strong compared to that, or at least it's been argued to be. And of course, this also, if this continues, and it's unclear exactly how this continues down to low redshift, maybe we don't see any locally, right? Which is maybe consistent with what we've been seeing for the last 20 or 30 years. Right? We have no analogs of these yet. This is just the number density again, but now comparing to old quasar samples. And so again, you can see that the sort of space densities of these objects are huge compared to the ground-based surveys. Right? So there's just a huge population of faint AGN that we didn't know about. And this has people thinking about revising reionization. Again, we had debated this for many, many years. Is it AGN? Is it star formation? And people had kind of decided, okay, it's going to be low mass sort of star-forming galaxies. And now they're rethinking it because of these things, these LRDs. Now, they may not actually pump out much UV, but there are a ton of them, and so we have to be careful. This is just showing compared to models, and so they still can be consistent with simulations, but just, right? So they're kind of maximally pushing the simulations if you seed black holes in these things. And in terms of seeding models, they tend to favor a light seed model, whether it be one that's super Eddington accreting or normally accreting. And this is a comparison of the evolution of, these are typical AGN, this is the AGN sort of number density from past like X-ray surveys, and then this is the number density from LRDs, and you can see this was dropping like a rock at sort of redshifts of 4 to 8, and these LRDs are just dominating by comparison at these redshifts. People have tried to do clustering of them, and they find generally that most big sort of past AGN has been sitting in relatively large halos. Right? This is what people have found. These LRDs, by comparison, seem to be sitting in relatively small halos. And so this might explain, for instance, why they have such a low stellar mass, but they're unusual compared to the AGN that we know and love. And so we have to kind of think about that. Right? So this is the sort of estimated halo masses of these objects. These are typical AGN from past surveys, and there's an order of magnitude difference in the sort of scaling of where they fall. Okay, so that's kind of a summary of the hundreds of papers that have been published in the last 2 years, which is a lot. And so I apologize for that, but there's some outstanding issues here that I wanted to kind of at least bring up. And one of them is the fact that they have relatively high black hole masses, they have low stellar masses, right? And it's sort of unclear whether we should trust the scaling relations or not. And I'll talk about some of the models, and you can have this in the back of your head as we go through some of these models. Because what you need for the scaling relation, basically, is that, right, what happens, why the whole scaling relation is just that you have some UV radiation, and it varies, and it moves out, and it ionizes the broadline region, and that will vary as well on a time scale which is comparable to the light travel time. You measure the light travel time, you get a radius, and you define a radius at which this material is moving around. You assume it's Keplerian or something approximating that, and you then use the full width half max of that line to get, essentially you say it's virialized, and you then can solve this and figure out the mass inside that, right? So will that work in these objects? We don't see any hard UV. We don't see it vary. We're not even sure what the structure of it is yet. It's got these weird envelopes, and so it's really entirely unclear what's going on there. The FCD is not typical, as I mentioned. It's X-ray weak, it's IR weak, it's hard UV weak. There's no variability, and so something else is going on. We can kind of explain it with this super Eddington accretion, but we don't have that many examples locally where we can pin this down. The clustering implies small halos. This is in tension with high mass black holes. The reddened component that I was talking about, we're not even sure what that component is. Is that an AGN continuum which is reddened? Is it something else which is reprocessed? What's sort of going on there? And then we have the issue that JWST has found these things. They're relatively faint, and it's outstripped every other waveband, every other resource we have to sort of throw at these things. And this is problematic because it means we're really limited in what we can probe. Okay, so I'm going to talk a little bit about models. So one possibility here is that you have we're witnessing basically direct collapse black holes. And so you have some compaction of a large amount of gas, and then as that is, sort of packing down due to gravity, you have some sort of inflowing material. It's supposedly very metal poor, or sort of pure hydrogen helium, and this sort of ends up forming a direct collapse black hole. You still have material which is pumping into it, and that might form this atmosphere that we're talking about. And then at some point, some of this material might collapse down into an accretion disk, and you start having some accretion. This kind of starts to eat out a cavity. Eventually, you may have some star formation that sort of happens here as well. And eventually, this thing blows out, and you end up with your sort of standard AGN. This isn't a perfect scenario because these things are in relatively low mass environments. So you end up having a really overmassive black hole in this case. Maybe that's fine. This explains the lack of X-rays, the lack of maybe IR. The envelope is reprocessing the disk information, and then you have some outer component which is providing the UV. That's sort of fine. It prevents feedback, which might again lead you to a high black hole star ratio. That's fine. However, as I mentioned, we see these absorption features that are outflowing, but we're not supposed to have necessarily outflows here, so that, maybe there's a geometric effect going on. It's sort of unclear. There's a variety of different models that people have proposed. There's tons of people who've kind of proposed tweaks of this. But generally, what this ends up doing is you have an atmosphere which has some sort of temperature, maybe some sort of extinction, and then you have this UV component which could be from the disk itself. It could be from an outer star formation. It's not really clear. Better spectroscopy might be able to tell you. So that's one potential model. This is called quasi-star or cocooned supermassive black hole, but its idea is it's a direct collapse to a supermassive black hole. Another option is to have binary black holes. And so here you effectively have a truncated disk of two accreting black holes. And so this gives you, it sort of eats out a portion of the accretion disk, and so you're missing that flux. And so that leads to sort of a smaller UV component and a sort of larger, say, optical near-infrared component. This will generate a V-shaped SED kind of naturally. You don't need to obscure it necessarily. That sort of works, but it's really fine-tuned to get the break at around the Balmer break, which we see as a kind of a ubiquitous feature here. And so basically all of these objects have to have a very similar ratio of these disks, which doesn't seem likely given they're going to have different orbits and different dynamics and things like that. It also doesn't necessarily explain the weak IR or X-rays. Another possibility that people thought of was a double disk. So you have basically a sort of stable disk and an unstable disk. And this again gives you sort of a ratio of the UV to the optical. And you can kind of play around with that. And I can't remember what units these are. But basically you get this break here, which is kind of similar to the Balmer break. Again, you have to kind of fine tune this to sort of get this to work. You can have maybe the strong Balmer break, you're looking through a wind, and weak ones, you're not looking through the wind. It's a little bit convoluted, but it's possible. Another option, which is kind of interesting, is it's actually similar to the direct collapse black hole, but it involves a supermassive star. And so here, basically, you're in sort of this pre-main sequence phase where you're feeding a supermassive star. It hasn't collapsed yet, and the stellar atmosphere of that supermassive star is now what you're seeing as the red optical continuum. And you can have a variety of temperatures, and these things can be 10 to the 5, 10 to the 6 solar masses. I mean, they're kind of unicorns in the sense that we don't really have any observations of them, but there are theoretical sort of predictions of them, and they kind of sit on the Hashi sort of side of the pre-main sequence, continually feeding, and you get a kind of conveyor belt where you're processing that material through the outer sort of components of the star, and it has huge convection. And so you churn up all of this interesting material. But you can generate this sort of continuum. You can generate emission lines, which are actually part of the atmosphere. And we see this in massive stars already, right? So in 300 solar mass stars, yellow hypergiants, we see this broad emission line, absorption features, and this sort of continuum. So this is kind of an interesting idea. There's some predictions that this should be variable because the atmospheres are pretty unstable, and so they should kind of have some pulsations and things like that. But they actually explain a lot of the features. We don't need, they don't generate X-rays. They don't necessarily generate really sort of a huge amount of far infrared radiation. They do have some envelope which will reprocess into the near infrared and mid infrared, but they're kind of interesting. Another take on this is actually to have an accretion disk with a supermassive star. And this accretion disk can then generate the UV if you wanted it to. And it can allow you to kind of play with things and maybe have emission out through the near infrared. And so it could further explain some of the SEDs that we see. But again, supermassive stars are kind of this unicorn that we don't really know if they exist or not. And so we're kind of invoking magic to really go after them. Now, one could also say that about the AGN that are quasi-stars, but yeah, essentially in both cases you have an atmosphere and you have something inside powering it, whether that is a massive star or a direct collapse black hole, and this massive star might end up collapsing into a direct collapse black hole. It's sort of unclear. Okay, so again, one of the fundamental limits is JWST itself, which I said it largely is outpaced other sort of facilities. And it would be really ideal if we could have brighter or more nearby versions of these. And so I want to take the last few minutes to kind of explore what options we actually have, right? Because almost all of these have been found with JWST. Do we actually have any local analogs? Okay. And so it turns out we kind of do, but they're rare. And so Yuri Ivzatov published a series of papers where he poured through thousands of Sloan, hundreds of thousands of Sloan spectra, and he found some objects which have broad H alpha, not really much broad H beta, so strong Balmer breaks. They have a red continuum. It's hard to see in these units. They also rise to the blue. Lo and behold, not at Sloan spectral resolution, but at better spectral resolution, they actually show absorption features in H alpha, in helium, in H beta. We looked at their X-rays and for these four objects, and they're X-ray weak. And so they're X-ray weak by an order of magnitude at least, and most of them have upper limits. Colin Burke looked at their variability, and they're not very strongly variable. Maybe this one is, but most of the other ones are pretty much consistent with being non-variable. And so they seem to have some of the properties that I just mentioned, but there are only four of them. Another sort of analog are something called blue hot dogs. So hot dogs are hot dust-obscured galaxies, and so generally those are very red objects. Ulurgs, hyperlurgs are another name for them. There's a fraction of them that show these blue upturns. And so you can actually see that the SED looks pretty similar. And in this case, particular Roberto Assef used a sort of polarization to actually demonstrate that this component is really strongly polarized. And so what we think we're seeing is basically the ionization cone, and we're seeing a fraction of the light being scattered towards us. And so, right, this is all AGN in this case. And then we have a sort of stellar component which maybe fits some of this rest frame optical emission. Matthew Stepney found another object. Looks fairly similar. We don't know if this has a high polarization. So a fraction of these could be, of the LRDs could be these things, particularly at the very high luminosities. And we do know that a few of the LRDs are detected in the X-ray, a few are detected in the IR. So at least a very small fraction, less than 10%, 5%, might be associated with these blue hot dogs. Recently someone did, a couple of teams did very sort of high signal to noise spectra of the objects from Izotov. And so again, you can see they actually went into the near infrared, and so they kind of matched the depth of JWST, and so you can see absorption features in many of the permitted lines now, right? Very strong absorption features in several of them. You can see these are the sort of velocity profile of the absorption features once you normalize them out. So you can see some differences between H beta and H alpha and helium-1. So they have somewhat different velocity components. You can see that this goes out to sort of 900 kilometers per second, which is pretty interesting. They have SEDs which match the LRDs. They're very compact. And what's interesting is they also show absorption in sodium D, in calcium triplet, in potassium. And these absorption features not always necessarily lined up with the hydrogen ones, but the sort of profiles of them are consistent with the profiles from these. And so we think actually what's happening is that material which is absorbing the permitted lines is also probably allowing this. And so this envelope that you see is leading to these very broad absorption profiles that we see in these things. And Lin et al. Made this model of this sort of envelope. They still want a black hole in the center, sort of accreting super Eddington, and then it's surrounded by this envelope of, say, 1,000 AU. For some reason, they put the broadline regions up here, which then totally screws up the 4/2 max scaling relation, but they don't seem to really mention that. They see a bunch of Fe2 lines in the gas, so this is all the blue there. And then another group observed the same object with a different spectrograph, and they note that there's actually some absorption features of Fe1, Fe2, titanium-2, some other sort of features which are relatively cool absorption features. And so they require sort of temperatures of 5,000 Kelvin, something like that. Their velocity profiles are distinct from the sodium D, from the calcium triplet. They're not an outflow. They're much narrower, very deep, in fact, deeper than stellar templates, which is kind of puzzling. And so it's sort of unclear what that means. And this was on archive last month. So we're still kind of digesting that. We actually have a spectrum at higher spectral resolution. We find even more Fe2 and titanium-2 features. And so this spectrum is riddled with these absorption lines, which is from this atmosphere. And so interpreting what that is, and in particular interpreting the abundances in that atmosphere, might be very telling for what origin we might have. And so we're still, this sort of jury's out on what exactly that is. We need some modeling with supermassive stars, which of course is, sort of future modeling that has to be done. But it's kind of an interesting way that this is turning. The only other problem with these analogs is that they're relatively low luminosity compared to the LRDs. And so there's it's unclear exactly if they're good analogs for the bulk of the LRD population. For the faintest ones, they're fine. They match. I have a student, Anastasia, who's looking at the HST images of one of these objects. And so we see, again, it has a sort of asymmetric sort of extended emission profile. This is from the continuum image. And so we can see it's kind of extended like this. I show a cometary blue compact dwarf where you can see a sort of, what would be a point-like object. And then it has a tail. And so we're sort of liking this to that. We fit this with several different components. This blue component here is a supermassive star. And so you can see it does a decent job. It doesn't fully fit the near infrared, but you add a little bit of dust at a certain temperature, you could fit that. And so it seems like it could at least be a viable model for explaining this. And you basically have a young, low metallicity star-forming region or star-forming galaxy with maybe a supermassive star in it. It's possible. We got better X-ray limits, and so we've pushed the X-ray emission down to the star formation region, so it's kind of consistent with a star-forming galaxy. Another group has, again, a different Lin, published a sample of green peas, some of which show similar slopes in the optical and UV. They show broad lines. They show absorption. They're relatively faint. Well, actually, they have pretty sort of similar bolometric luminosities to the lower end of LRDs. They are on the BPT in kind of the right place in the star-forming region. So they might be, a few of them might be viable candidates. And then finally, I'm looking through all of local imaging, basically redshifting all of the LRD templates to try and find the parameter space where we might be able to search for these things. So far, I have 1.6 million candidates that I have to go through. Now, 200,000 of these actually are in DESIDR1. Another 20,000 are in Sloan. But however, when we actually, by doing this in redshift chunks, and I require that the spectrum be in the same redshift chunk, and when we do that, we find that about 75% of the candidates here are junk. They're in the wrong redshift. Then when we actually look at the spectra, we find that most are just standard AGN. On the BPT, for instance. If we look at their morphologies, they're kind of in dwarf spheroidals, in spirals. There's not much star formation going on. That may be OK. Many of them are radio AGN with broadline jets, or broadlines that are related to jet outflows. Many of them have very high ionization parameters. We see neon 5 in many of them. Sometimes the neon 5 is brighter than H beta. So they're also weird, but they're weird in a different way. And then we have lots of emission line galaxies that aren't broad. So from this, we have a few tens of candidates. And I'm saying candidates in quotes because it's really not clear how many features we need in order for it to match what an LRD is. And so we're still kind of working that out. OK, so with that, I just wanted to conclude. I think I've hopefully interested you and not bored you too much. And so I think in terms of conclusions, I don't have a strong one. Basically, I think we have a mixed origin for LRDs. At the very luminous end, probably some of them are associated with what we call these blue hot dogs, or these hyperluminous galaxies. What are the rest at the very luminous end? I'm not sure. There's definitely a cooling envelope, or sort of a cocoon envelope that's surrounding them, that's kind of giving off this very strong Balmer break in many of these. What's inside of that is unclear. Is it a supermassive black hole? What is its mass? That's uncertain. Is it a supermassive star? Would this supermassive star need to collapse to a supermassive black hole? Not necessarily. I mean, it could actually have a huge wind at a later phase and become basically a self-enriching globular cluster, which is an interesting theory that JWST sort of published back in 2018. And this would actually solve a completely different problem, which is the multiple populations in globular clusters. So it's unclear what the connection is there, if there's a connection at all. Maybe we're completely wrong and there's still something else out there that can explain these things. OK, so I'll leave you with that and take any questions that you might have. Thanks. Obscured versus intrinsic.
Yes. So I know that these sources are very fine in X-rays. So, but did you try a new star observation above 10 keV?
For the high redshift ones, no. New star is not sensitive enough.
But for the local
So G et al. Did do a DDT observation with new star and put a limit on it. It's not a super strong limit compared to Chandra's limit at sort of 2 to 10 keV. The 2 to 10 keV limit, this is for a different object, so they did it for 1025. It's kind of sitting here. So it's below the relation, but not, maybe an order of magnitude. It's an upper limit. They don't have detection. So it's not as strong, but it's still kind of X-ray weak. Like it, you might not even see anything in new star.
And you should observe something above 10 keV.
If it's 10 to the 24, you might see something above. If it's 10 to the 26, you're hopeless,
yes,
right?
But even with new star up to 80 keV,
Yeah.
that is maybe too fine.
I mean, the limit they I don't have it in a slide, a backup slide. But basically, if you look at the sort of 10 to 80 keV or 10 to 30 keV, I don't remember exactly what they used, it's still sitting kind of below the extrapolated, but you have to also note that this isn't calibrated for new star, so we don't really know where objects sit on that, right? What star formation really is at 30 keV. So there's lots of unknowns there, but they can place a constraint that suggests it isn't, if they put that limit and they extrapolate back what would be an unobscured AGN, it's still sitting below what we would think this relation would provide. So it's X-ray weak, but not strongly X-ray weak. Okay.
So what's the expected timescale for the variability of the supermassive stars, and could we miss it in the observations that we have here?
Right. So I think it's sort of unclear. So the variability arguments kind of come from massive stars that are, say, 300 solar masses, where we do see some variability, and it's by like factors of 2 on timescales of years. And so it's unclear whether scaling that up to 10 to the 5 solar masses, how that translates. And so we obviously don't have any empirical examples yet. And so yeah, it's a big question mark, really. I can't really say exactly. I mean, you do have, the thing is, you have lots of convective zones, very large convective zones. It's kind of convection dominated for a part of its life, and so you could see some sort of variability just from the convection, but that's kind of going to be at a low level. And so I think you also, from the hypergiants, you see like outflows. I mean, Eta Carina had like an explosion at some point. Like you would definitely see that, but you would need a lot of them to maybe catch one of those explosive episodes. And we don't have a lot of them at the moment.
And in the observation of JWST, how many times do we have the same objects?
So I mean, several objects have been observed like twice or 3 times, just as part of the, this is a survey, we hit it a couple of times. So yeah, they have sort of some measurements, but then the calibration uncertainties end up being like 0.3, 0.5 mag, depending, different orientations, different whatevers. And so you had to have like, we see it vary by 0.5, but then the error is 0.4. And so if you could calibrate the JWST data better, maybe you could push that down and start to actually see stuff and place some constraints.
At the beginning of your talk, you said that the UV part is variable, is different from the large.
That was my claim, at least. In some models, no.
Yeah, the point is, this variability is explained. For example, is it a different consistent with a different attenuation, or is it the level or the slope, and does it induce any models to explain the
Right. So let's see if I can zoom back through all of this. But good enough. Yeah, let's see. Yeah, sure, here. Well, so, yeah, so if this is star formation, and it's kind of distinct from the cocooned whatever it is, then we don't expect the star formation to vary. We don't expect this to vary at all. Maybe we expect this to vary, but maybe if you have a cocoon, that's going to damp everything. And so maybe the lack of variability is from the cocoon. Right? So you can kind of explain it that way. If this was scattered light from an AGN, then again you're going to have a damping because, say, you have an ionization cone and you're getting a scatter, that's going to dampen it by the size scale. And so again, maybe we're just not probing variability on long enough time scales to see that. There is one object which is lensed with multiple lenses, and those light paths are different by, I want to say, a few hundred years. And there we don't see variability at higher than a sort of 20% range, and that's mostly due to calibration issues again. So yeah, I think there are ways to explain it from the model point of view. The data aren't good enough to necessarily fully constrain and say there is variability at a small level. So yeah. Well, sir?
Well, I have a very nice question here. Have somebody explored the model of, let's say, primordial or low metallicity starburst, where suddenly the dominant stellar population becomes a red superior. So in this case, you have a kind of natural mixture of stellar populations where the red part of the spectrum will be dominated by these stars, and you still have the basic, a little bit lower metallicity
Yeah, so
stars in the blue.
yeah, I apologize that this isn't very good resolution, but this is one of the models, basically two stellar components. This is from Ivo Labe. And so one of them has a stellar mass of 9.8, another one has a stellar mass of 10.8. Both have extinctions of around 0.5. And yeah, you basically had a burst of star formation which created this thing. But you have a hard time explaining the Balmer break there. It's just too steep for some objects. For other objects, it's fine. You can kind of explain it because this isn't.
With normal, let's say with normal solar metallicity kind of
I think they've probed down to, I don't know if they probed down to like 0.0001.
very low metallicity ones,
Yeah.
it makes a difference.
Yeah.
So yeah, I have to read the paper.
Yeah. I mean, the problem is actually staying up to date with the literature because there's like almost a paper a day. So yeah. Any other questions? Again, I'm going to be here all month, so if you want to talk to me about this or anything else, feel free.
Any questions? Okay, so let's thank Frank again.
Hi.
I was a student at Católica, so I just wanted to come say hello.
Hi, nice to meet you.
I did my licenciatura there.
Okay, with,
I worked with Cristobal Petrovic. Mainly.
okay, before he left, yeah.
Yeah, before he left. And then, there's Gijs Mulders now replacing him.
Yes.
And I worked a lot with him.
Okay,
In
cool.
fact, we published a few months ago.
Nice,
Yeah.
congratulations.
Yeah.
Yeah, Heis is very good. I mean, he's a very good hire.
great guy.
Yeah, I like him a lot. I mean, I'm sort of sad that I moved because I like my colleagues a lot, but
Yeah.
I moved for other reasons. So
Yeah, there's a lot of great people there.
yes.